this semester, we've talked about batch and flow reactors, right? And in that development, we've always made certain assumptions about how those reactors operate. So, for a batch reactor, for example, we've always assumed that, we had complete mixing, right? That the concentration of all the species are homogeneous everywhere, right? So the concentrations are the same everywhere, the temperature is the same. And what that meant was our reaction rate is the same everywhere inside of the reactor. Okay. And for CSTR, we also made assumptions. And it was not only that we had perfect mixing, but it's also that, so we had this, but it's also that it occurred instantaneously, right? As soon as we added something into the reactor, it became perfectly homogeneously mixed. Temperature was the same everywhere inside of the reactor. And let's think about what that might mean for a CSTR when we do a couple of things to it. So the first thing that we will do is, let's say that we just introduced a pulse into a CSTR. And what I mean by that is that, we have our reactor that's operating, right? And, I'll draw this like a liquid CSTR. And we have some flow that's coming in and we have some flow that's going out. And what we do in a pulse is that we have this sudden injection of a tracer, right? Some tracer T. And the reason that we call this a tracer is that we are going to sort of trace the response of a sensor at the inlet. So this is a sensor. And we'll also trace a sensor at the outlet. Okay. Sorry, that does not look like much of any. And what we're going to be able to look at then is the concentration profile at both sensors as a function of time. So let's take a look at this sensor first. And if we added a pulse, right, we're just, I guess, squirting a little bit in, right? So if we looked at this, right, CT in, and then we looked at the concentration as a function of time, right? Here's our sensor. And let's say that we did this at some time equal to T1. Well, at the beginning, right, we turn the sensor on, we wouldn't measure anything. All right, so we'd measure nothing. And then all of a sudden, right at T1, you would see a pulse. And then it would go back to 0 and move on, right? And this is, of course, an ideal case. And if we looked at the outlet, well, what would happen? Well, let's do a very similar thing, right? So let's look at the outlet sensor. And we're going to measure the concentration of the tracer as a function of time. And we have, some time T1. And then the other time that is important here is T1 plus tau 1, right? And maybe I'll call that tau 1 star, where tau 1 star is just the reactor volume divided by the volumetric flow rate, right? And right, it's the initial volumetric flow rate. And if we looked at this, well, what would happen? Well, at time equal to 0, of course, we haven't put any even into the feed yet. So we don't see anything, right? So we get all the way to T1, we don't see anything. Now, the pulse is in the reactor, right? We've put it in the reactor and it homogeneously mixes. And you get some average amount of time that the tracer is going to spend in the reactor, and then it's going to come down, right? And it'll trail off to 0. And so when we have a pulse input, we have some expectation for what might happen if we added a pulse into the system in terms of the concentration of T here, of our tracer, okay? Now, what about flow? Well, we could think about this if instead of pulsing, what I mean by flow, maybe flow is a very bad way to say this, but how about a step change in the concentration? That's probably a much better way to think about this. In chemistry, we talk a lot about a step change. So let's say we did the exact same thing at both sensors, or we took a step change and we measured what was happening at both sensors. Now, as a function of time, we have the concentration of the tracer in, and at some time equal to T1, right? We start at 0 and we go to some concentration, okay? And we'll call that, CT0. And now we're going to measure the concentration of the sensor during that step change. So that's CT out. And what's going to happen? Well, if we were to measure this, right, again, we have two characteristic times, right? We have T1 and T1 plus tau 1. And so what's going to happen when we do the step change? Well, you have some amount of time after that where the concentration gradient develops. So you're going to get all the way out to here, right? That's still going to be equal to 0. And then at some point, you're going to start to see that the concentration at the outlet increases, but it doesn't do so in the same step change kind of way, right? It's going to be mixed, it's going to come out, and then you're going to reach steady state at some point in the future, right? We're not operating at steady state in a tracer experiment like this yet, right? This is the steady state. And what you're going to measure is that it's going to come up and it's going to level off, okay? Now, this is in an ideal case where you would start to observe the concentration of the tracer increase in very, very predictable ways. And the book is very quantitative about this. They have these functions, E of t, F of t, for example, that they use to be really quantitative with what's happening. But I don't necessarily want to do that here. We'll end up being semi-quantitative later. But the thing that I want to get across here is that in a real system, what normally happens in the response is that you have a much broader distribution. So one of the things that you could have, for example, and I'm going to draw this in red here for a pulse input, is that you see something that looks more like this. And what's happening here? I mean, we have a premature arrival of the tracer, and it also lingers for a much longer time than we thought that it might. For flow, for example, you also could have the same thing where it starts out at about 0, and then you lazily come back or reach the steady state at some point here. And the reason that this would happen is that because despite what we've said so far during the course of our semester, there does not exist one residence time. There is not one amount of time that a species or that every species spends inside of the reactor. In fact, there is a distribution of residence times. And this distribution of residence time happens because the flow pattern is not ideal, right? In a CSTR, right, we have mixing. And we say, okay, look, it's going to be mixed instantly and homogeneous everywhere. But that can't happen in a real device. If you think about very, very large reactors, there are a couple of things that maybe jump out to you almost immediately as possibilities. The first thing that can happen is that your reactor can have dead zones. And dead zones are effectively areas of your CSTR that are poorly, or your reactor that are poorly utilized, because this doesn't just have to happen in CSTRs. It can happen in batch reactors. It can happen in plug flow reactors. And so now let's say that we have, we have an impeller here, and we have our flow coming in and our flow leaving. Well, if you looked at this and I told you that there are areas where the mixing might be poor and therefore unutilized, what might you guys guess in this simple illustration? Where might you have a poorly utilized volume?
Maybe like the bottom corners.
Yeah, the corners are a great place, right? So let's think about it like here, right? All right. Yeah, that seems to make sense, right? You also could draw one here. It's also possible to have them at the top and at other places. So these dead zones, right? And that's really what these are, right? What they do is they effectively reduce the volume, right? This thing like VS, right, that we're going to end up using this, is less than the reactor volume. And that's not good. If you think about this in a CSTR, if you made the effective volume lower, you would make the residence time lower, right? Because remember, we wrote above that tau is equal to V over the volumetric flow rate. And if you made the residence time go down, you also would have the conversion go down, right? And this is bad, right? So your reactor might not be able to behave as you thought that it should. Another problem in CSTRs are areas where you have short circuiting, or it's also called bypass. Okay, and when that happens, essentially you feed something into a reactor, and it actually happens a lot when you say, oh, let's add another impeller to improve mixing, that you get vortexing and other weird things. And so then what happens is that it would come from the inlet and it would go right to the outlet. It would never see the other places in the reactor. And so when that happens, again, the effective residence time for this stuff in green would be less than it should be, and therefore your conversion would decrease, right? Because essentially some amount of the flow never was introduced into the reactor to begin with. You basically just put it directly from the inlet into the outlet. And the third thing that you can have inside of a reactor is backmixing. And the idea behind backmixing is that now, let's say you become well incorporated into our volume, right? So you've come in and you've gone around, you're homogeneously mixed, but instead of heading to the exit, you just go and hang out up here for a while. And then after that, you come over here and you hang out here for a while, and then you go to the exit. Now, in that case, the residence time is much longer than you thought it was going to be. And these species end up having a higher conversion than you might have otherwise thought, but that comes at the detriment of other areas of the reactor. And so, these three mechanisms work to manipulate the residence time of reactants inside of the reactor, and they make them operate in ways that are not predictable necessarily by the things that we've done so far this semester. Okay, so before I move on, I talk about this a little bit more. Does anybody have any questions that they want to ask? All right. So a second ago, I said that your book defines this function. Maybe I'll leave this here so we could see it. E of t. And we're not going to deal with this extensively. So this is in chapter 16. And they define this function basically as the concentration as a function of time divided by the integral from 0 to infinity, right, or infinite time of this thing. And C of t here is what you measure. right? That's our experimental data. And what that does is it normalizes everything on this basis of 1. So the integral from 0 to infinity of E of t is equal to 1. And all that this says is that over an infinite amount of time, we're able to measure everything that we added into the reactor. And they like to do this. And actually, these E of t functions can be pretty helpful, where let's say for a CSTR, if we looked at that function with time, well, let's look at 2 cases maybe. I'll draw one line, I'll call it the ideal case. And remember above, right, that some concentration enters right at the beginning, right? So if we started this plot at T1, so you would measure some concentration at the beginning, and then you're dividing that over the integral from 0 to infinity. And so you get a response that actually looks kind of like this. And then if you had a non-ideal case, it would deviate from that. And it could deviate from that in a number of ways. So one, you could have one that's kind of close. And let's say you start a little bit low, you end a little bit high, right? So you end up, sorry, that one wasn't particularly great. But let's say you start off like that. Okay, that's somewhat close. But let's say that we had a case where we had short circuiting. What would that mean? Well, that would actually mean that if we're measuring the concentration of, let's say, a tracer or our reactant, well, if you had short circuiting, you would have a bunch of it that would not be, that would not react. So it would be really arbitrarily high at the beginning. So you might actually see something where like it comes up and then crashes eventually, right? Or comes up and then never quite gets to the low concentration that you thought, because your final concentration in the reactor is higher than it was at the beginning, or higher than it was in the ideal case. And the same thing can happen for, oh, sorry about that. I actually didn't mean to do that. And the same thing that can happen for a plug flow reactor, right? So let's think about this for a plug flow reactor. So in our PFR, remember that everything moves as, a 2-dimensional cut through this, right? And then over some time, right, it moves literally as a 2-dimensional plug. So in a PFR, our E of t is very simple. That we have 1 residence time, right? So if we looked at this in the ideal case, we would just have a straight line here, and that would be at tau. But if we deviated from this, right? So you had, let's take a non-ideal version. Well, actually, you could have an E of t that was broad. You also could have one. Let's say that we had short circuiting and back mixing, right? You could have an example where here, the short circuiting is going to come out very early, right? So you have some residence time related to short circuiting. And then after that, let's say that you had something like back mixing, right? And now all of a sudden you're designing a reactor around this residence time, but you actually have 2 completely different residence times inside of your reactor. And so the question then is, how do we deal with these, right? How do we deal with the fact that we have these distributions of residence time and we have species inside of our reactor that are behaving differently than our assumptions? Well, when that's the case, there are a bunch of approaches that can be tried. But one way to do this is to actually look at reactors as either combinations of ideal reactors, or to start looking at other ways to incorporate things like short circuiting and dead volume into into our models or into our understanding for how how our system is behaving. So I'm just going to show you a couple of examples here. And so we'll start here on the left-hand side. So this is like a packed bed reactor or a plug flow reactor with dead volume and bypass. And that's the thing that's trying to be shown here, that you have some areas where you're clearly just going through the reactor, right? Or you have mass transport in that direction along with the flow. And then you also have areas, let's say this is between catalyst particles, where you just get trapped, right? And so you have dead zones. So how might you model something like this, where you know that you have a packed bed reactor, you have channeling or bypass, you also have dead zones? Well, the model, or one model to do this, is shown sort of right below that here, where we would make a process flow diagram that is a little bit different than just one single reactor. So we would have some portion of this volume, Vs, that we would solve exactly like a plug flow reactor, but we would do this, or a packed bed reactor, but we would do this at a reduced volume, right? And V sub D here would be the dead volume, right? These areas. And then we also could take into consideration that you fed part of your initial volume, some of it goes through the packed bed and some of it does not. And so you end up looking at what's happening inside a reactor with a reduced volume, and then you end up analyzing what happens here. So you actually have this point where you have a split, then you have a reactor with reduced volume, and then you have a mixing point. And this is where what you guys did in 300 comes in really, really handy and allows us to solve for non-ideal reactor problems in this way, where you just make a simplified process flow diagram, and then we do the same thing that you would have done in 300, where we do mass balances, right? Where these would be 300 mass balances, and these are the mass balances that we've spent our entire semester working on so far. So those are really interesting models. You also can have a model that well represents data where you might just have two different residence times. Let's say one near the wall, where you have more friction, and one in the center where it goes through the reactor very, very quickly. Well, when that's the case, it sort of behaves just like you see on the top right here as two totally different plug flow reactors. If that is the case, let's just model the system then as two plug flow reactors in parallel. And the first reactor takes up a portion of that volume, and the second reactor takes up the rest of it, right? Because the sum of these two is just the volume. And you also have some fraction of the flow that goes through this top portion, and some portion of the flow that goes through the bottom portion. So here's a couple of examples for PFRs. Another one might be that you have back mixing inside of your plug flow reactor. And so some of it has a residence time that's a little bit different than the primary plug. Well, when that's the case, then maybe we could think about it as almost like a CSTR, where CSTRs are well mixed everywhere. So you have some aspect of well mixing in the PFR, maybe because it's not laminar, for example, that you have turbulent, like highly turbulent flow. So you might model that system as a CSTR and a PFR in parallel. And if you remember, we did some of this earlier in the semester where we had CSTRs in series, we had CSTRs and PFRs in series, and you also could split the flow and do these things in parallel. And CSTRs have this as well. So a couple of models related to CSTRs are sometimes you can have different areas of mixing inside of your CSTR between the inlet and the outlet. So instead of solving the problem as just one CSTR, well, maybe you just model it this way, that you have just three, in this case, because you have three impellers or three regions, you might be able to solve the problem as three CSTRs in series, which we've actually solved that problem in class. And then you also could have intermixing, which really just means that instead of going into the inlet being homogeneously mixed immediately, it was the purple line that I showed just a minute ago, where some of the stuff stays in the reactor a little bit longer. And that stuff also takes up some amount of the reactor volume. Well, that could be modeled actually by a CSTR in parallel with another CSTR, where some portion of the volumetric flow rate is intermixed, right? Goes into a second zone or reactor, where then some reaction happens. It ends up eventually back into the primary reactor and then out. And you end up in this particular case, doing mass balances on the reactors and then again at the mixing point before it comes out. And they're just slightly more complicated mass balances than we've done before. And the last model that I will just show you is a CSTR, a single vessel with bypass and dead zones. And so here, right, you see that you have fluid coming in, some of it just immediately leaves, and some of the volume is totally unutilized. And just like somebody chimed in earlier in the lecture, right, it's in the corners, right? They draw this on the bottom and in corners for a reason, because that is primarily where it would happen. And when that's the case, our process flow diagram can simplify to being our reactor. And then just like I showed earlier with the PFR, we have a split point here that's labeled as 1. We have another split point here that is labeled as 2. And this model, a CSTR with bypass and dead zones, we're going to spend some time on. I'm going to talk about it a little bit more now, and then we'll talk about it in the next lecture as well. Before I do that, though, I know that we just sort of rambled through several different models, and depending on what you would notice when you measured the concentration versus time, you would pick one. Do you guys have any questions about what I've done maybe the last 10 minutes before we deal with this type of reactor a little bit more, or this model for a CSTR a little bit more?
So when it comes to like which model you would pick, would you kind of provide us with that, or is there a way to kind of like look at data maybe and tell?
Yeah, that's a really good question. It is possible to look at data and to be able to tell which model. And sometimes the data is, if you get the concentration versus time, right? Some just look at this. And for example, when they see that you see a whole bunch of the concentration of what you were measuring come out at the beginning, and then it goes to 0, they said, oh, it just bypassed, right? And that's why that is there. Then you see something that looks a lot more reasonable for the concentration leaving a plug flow reactor over time. And so they said, okay, well, some of it behaves like this, some of it behaves like this. And we'll get some practice this semester with both of those, where, I'm not going to lie to you guys. We all know that, you guys will have quiz 8. It's going to be on non-ideal reactors, because that's what we're talking about. And in that example, I will say, or in that quiz, I will tell you, this is the model to follow. I believe that's the case on the homework problem as well, that you're told what model to follow. So that's going to happen, for now. You guys do not need to reinvent the wheel on models. So it will either be a model that's very obvious, or you'll just be directly given a reactor is behaving in along this model, and please analyze these parameters or determine the conversion. Okay.
All right, thanks.
Yeah, I'm not going to get into the business this semester of doing something really advanced, like giving you a complicated concentration versus time and then say, hey, you guys go figure it out. An advanced course, that would be okay, but I really want you guys to get the concept of this and not get bogged down too much in complexity. Okay, good question. Any other questions? All right, so then let's deal with this model a little bit more. okay? Because the next lecture is going to deal exclusively with this model for a CSTR. And what we have, right, is our reactor. And we know that we have bypass and dead zones, okay? And there are a couple of ways that we are gonna look at this. So first, I'm gonna draw just a simple diagram, and then we'll kind of take it from there, okay? So there's our diagram, and in we have some concentration, let's say of A, right, which might be our reactant, and we have some initial volumetric flow rate. And at this point here, we are going to split. And to do that, we're going to define a term. So we're going to say that this parameter beta is equal to the volumetric flow rate that bypasses the reactor divided by the initial flow rate. Okay, so this is like the fraction of bypass. So then if I were to label this on this stream, right, this is still CA0. And then this is V sub B, which of course, as we just said, equals V0 times beta. Okay, so all we've done is split the stream. So then this here, we're going to call VS, the part that doesn't get split. And so of course, by extension, right, because we know that V0 is equal to VB plus VS. Well, that means that VS is equal to V0 minus VB, which is just V0 times 1 minus beta, right? That makes sense, right? This is just the fraction of the flow that did not go through the bypass, okay? So now we've split the flow and it recombines here. But remember, when this comes out, we are at the same initial volumetric flow rate, right? Once we reach steady state, just like you did in 300, we have to be able to draw a balance all the way around here, right? And so the concentrations times the flow rates are all going to be equal to each other. Now here we have CA0, there's some reaction happening inside, so we'd have mole balances and stuff. But to draw the box all the way around the outside in a liquid reactor like this, that V0 has to be equal to a constant, or if delta N equals 0, for example. So hopefully this is okay. So now what we're going to do is say that, look, we also have part of our reactor that has dead zones. And I don't know a great way to do this other than to just say, look, this is V sub D, and that's the dead volume. And we are going to define a second term. So we're going to say that alpha is equal to the portion of the reactor that you're actually using, which we'll call VS, divided by the actual reactor volume, which is V. Okay. So then VS here equals alpha times the volume. And that would mean then, of course, because the volumes have to add, that, right, because V sub D is just going to be equal to the volume plus, oh, sorry. Here, let me do this a different way. So the volume is equal to VS plus V sub D. So that means that V sub D equals 1 minus alpha times the volume. Okay. Maybe that makes the diagram look a little messy, so I'll get rid of that because it's over here on the right-hand side already. Okay. So we have these parameters, beta and alpha. And because of this, if you go to look at this in your book, you know, this is an example of something called a 2-parameter model. And normally what you would do is you would do a tracer experiment and you would determine alpha and beta. And in the next lecture, we are going to do that. So we'll solve an example just like this, and then we'll solve an example where we have experimental data and we have to determine alpha and beta. Now, the thing I want to maybe talk about before we end today is how would you solve a problem like this, right? Because we're going to have two different concentrations here. So we have some reaction or some concentration coming out of the reactor, right? CAS. And then we also have some concentration A. And when we want to think about conversion, right, that's 1 minus CA over CA0. And this is this CA. And this is this CA0. And so how are we going to do that? And we're going to take two steps to solve these problems, and especially in the two parameter model. So the first step is that we are going to do a mass balance around the reactor. And then we're going to end up solving for this intermediate concentration, given what we know, right? We'll already know beta, we'll already know alpha, okay? And then the second thing that we're going to do is we are going to solve the mass balance on this point right here. Your book calls it point 2, but we'll just say we're going to solve the mass balance at this star, okay? And if we were to do that in this case, right? So let me zoom out a little bit. Let's just start to take a look at this a little bit. So let's just solve the mass balance for the reactor, or at least write the mass balance, and then we'll actually solve it next time. So in the reactor, or at the reactor, or sorry, I was right the first time, in the reactor, we have our mass balance, in minus out plus reaction equals accumulation, right? And now for a CSTR, we actually know that we can get rid of this, right? We're operating at steady state. So in minus out plus reaction is equal to 0. And now let's think about what's coming into the reactor. Well, coming into the reactor, we're at VS times CA0, right? Right, so that's V times S times CA0. Then minus the flow that's leaving, that's also VS times CAS. And then plus the reaction term. And so let's say that we were looking at this as just RA equals minus K1 times CA, right? Well, our reaction term, right, is plus RA times V. So this becomes minus K1 now times CA, but it's CA inside of the reactor, times VS, the volume, the effective volume of the reactor. That's equal to 0. Okay. And so we have our mass balance here. And the next thing that we'll work on in the following lecture is now, how are we going to get this in terms of alpha and beta? And then we're going to solve this for CAS. Okay, so we're going to do that in the next lecture. Now at the mixing point here, this is the star that I squared in red. We have a much easier mass balance to solve, right? So we have in minus out plus reaction equals accumulation. But at the mixing point, right, we're operating our reactor at steady state, that's 0, and there's no reaction that's happening at the mixing point. So we just end up with in minus out is equal to 0 at the mixing point. So let's sort of zoom in on that mixing point there. Well, coming in, right, we have two streams. We have one here and one here. And then we have one stream that's leaving. So we end up with CA0 times the volumetric flow rate that went through the bypass, right? That's this stuff coming in here, plus the volumetric flow rate of what is coming out of the reactor at the concentration coming out of the reactor, minus the overall volumetric flow rate times the concentration that's actually leaving. That would be leaving the real reactor, not just the effective concentration or the concentration leaving the effective volume. So that's times V0. and that's equal to 0. And so when we actually solve a problem with this next time, we're going to do something very similar to what we're going to do here. We're going to get this mass balance in terms of alpha and beta, and then we're going to solve for Ca, and then we're going to use that to solve for the conversion.